So we're going to talk about logarithmic function. So the logarithmic function is the inverse function to exponentials, and so it kind of flips the question on its head. And so we're going to let a be greater than 0 and a not equal to 1, same reason we did before, that we don't have to deal with complex numbers. So a logarithmic function base 8 is denoted as log base a. So log base a equals y is the same thing of saying as a to the y equals x, right? And so, and remember what an inverse function does. If I have f of x is y, then f inverse y will give me back x, right? And so if I pull something out, I put it back exactly where I found it. So to me, an inverse is a good library, right? A human comes and takes out the book, and the librarian puts it exactly where it went back, right? So here, so these are inverses of each other. We'll get into that in a second. So the log asks this question. And so in order to figure out how to answer that question, it's easy. This is when mathematicians solve logs in their head, they're actually solving this in their head. They're not solving this, they're solving this, right? Because that's what it means. And so they're just kind of crunching through what this means. And let me explain that by actually showing you. So log of 10 of 1,000 is 3. But let's pretend I didn't know what it was for a second. That means 10 to what? What is 1,000? Well, 10 to what is 1,000? Well, that's 3, right? So that's how they solved it in their head, okay? Here, if I was going to rewrite this would be 2 to what power equals 64, right? Because that's what this question is asking. Log of 2 is 64. What power of 64 is 2? And the correct answer here is 6. Here, the log of 16 asks 16 to what power is 4? And what power that is a half, or the square root of 16 is equal to 4, right? And so what log functions are doing is they want to ask, this is what power of my base, right? This is what power of my base. So 1,000 is what power of 10? Well, 3. 64 is what power of 2? 6, right? 4 is what power of 16? A half. So that's what a log is, right? And just so you get more comfortable with going back and forth, I'm going to ask you to do a couple of these. So here 10 to the first -1 power is 0.1. So the log equivalent of this is log of 10. So my base is here. So here all my logs will be the same base, right? So I choose the same base. So the base comes here, right? What it equal to is now my question. And then we'll go through this slowly. So log of 10, so 0.1. So 0.1 is what power of 10? Well, it's 10 to the minus first power, right? 125 is what power of 5? Well, it's 5 to the third power, right? We have the answers up here, but if we were just doing it in our heads, 81 is what power of 3? Why, that's 80, why, it's the fourth power. So it's 3 to the fourth power, okay? So that's what it means to be a log. All right, so let's graph it. Let's go ahead and graph this. All right, so I'm gonna graph, so I want you to, so here we're gonna graph both log of 2 and it's the inverse function. So we'll go through this. All right, and so here I'm gonna do certain things. So here I'm gonna make my x's easier to graph, that way I know what I'm doing. So here I'm gonna have x, so x of 0 is 1. So the log of 1, so log of 2 of 1 is equal to what? Here I'm asking the question, log of 2. 1 is what power of 2? Well, 2 to the 0 power, right? Here I have a log of what power, a log of 2 to what power is 2? Well, that would be 1, right? And then here, if I have 2 to the second power, that'd be 4. So x, here I can plug into. Here, I can do this game again. So I can have log of, and here I'm going to say 2 to the negative 1 power, which is equal to a half. So x is a half. That's going to equal to what? Well, that's going to be negative 1. And x equals to, or 2 to the negative 2 is equal to a fourth. That's negative 2. Because here, if I put that in, log of 2, a fourth is what power of 2? Why, it's negative 2. Negative 3 and negative 4. And so here, this will give me an eighth. This will give me a 16th. And here I'm going to have minus 3, minus 4. Okay. So let's graph this. Let's graph this real quick. So as we graph this, we're going to have here, I'm going to be at, let's graph this one. So at 1, I'm at 0. At 2, I'm at 1. At 4, I'm at 2. At a half, I'm at minus 1. At minus a fourth, I'm at 2. At minus an eighth, I'm at negative 3. And then minus 4. And so if we actually graph this in, it looks like this. Okay. Actually, I should hug this line a little bit better. Oops, I'm on the wrong one. Get on the right layer so I can erase. Let's go ahead and do our second one in teal. So here, if we're going to graph this, we already know what these points are. Here it's at 2. Here, or no, it's at 0, 1. All exponentials go through 0, 1. The next one's at 2. The next one's at 4. Next one's at 8. And then here, half. So we have it look something like this. So there's our exponential, which we graphed before, in different color. So notice that I'll teach you something right now. We didn't go over it, but it's good to know in your head. So here, this is the y equals x line. Inverses are reflected across this line, okay? So an inverse is a reflection. So here, this distance here is this distance here, this distance here is this distance here, if I drew it correctly. This distance here would be this distance here. So these are equal distance from each other all the way through, okay? So once we have all this, and so we notice that this is just an inverse of this. And so all these graphs look like this. So no matter what you're graphing of log, they all roughly look like this, kind of like all exponentials roughly look like this. Let me just go over one thing that's real important. What is the domain? Let me do this in black instead of hot pink. What is the domain of the log? Well, the domain here is, can I have negative numbers here? Or another question is 2 to any power? Hold on, let's go up to it. Let's go up. Let's look right here. No. Is 2 to any power going to produce me a negative number, right? Like negative 1. Is there any way I can get that? The answer is no, right? Because even if I put in a negative 1,000, I just get really, really, really small, right? But I'm not, because this would be the same thing as 2 over 1,000. This is really small, but I never can change the sign. So this never becomes negative. And so the domain of logarithmic functions is, here if I have log base, whatever my base is, b of x, x is strictly greater than 0. Or if you put it in, come on, do as I want. Of course. Fine. Or to put it in interval notation, be 0 to infinity. Okay, so there is no number which makes it 0, and it goes all the way to infinity. Okay, let's go do this. I do want to talk about domain for 2 more seconds, so let me just continue that thought up here. Yeah, let me continue that thought up here. So here, if I had the log base b of x minus 4, here we say x minus 4 is strictly greater than 0, which we could solve to be x is strictly greater than 4. And then here we'd have 4 to infinity. So that's how you find the log. You'll have at least one question on the exam to find the domain of a log function. Okay. All right. I asked the question, someone answered no, and I forgot what the question was. Sorry. All right. How are you guys' comfort level with logs? Have you seen some of this before, or is this all new? It's new. I'm good with this. Seen before. Okay, so some of it's new, some of it's not. We'll go kind of slowly for a little bit, and then tomorrow's going to be the kind of harder day, and we'll get through it as slow as we can. Yeah, if you've seen it before, the essence of learning is repetition. For anyone who's done study as a sport, you obviously know that. You go do the same thing over and over and over again, fixing it. What's the old sport mantra? It's focus, feedback, fix. That's what you're supposed to be doing during a practice. You focus on what you're doing, you get feedback from either a coach or yourself, and then you fix it, and then you go back in this loop. Because practice doesn't make perfect, practice makes permanent. So perfect practice makes perfect, and so that's what you need to do. All right. Will you upload the video for the class? I'm going to upload these things. Because graduation thing. Yeah, I'll upload the class to tomorrow. That way it's sooner than later. Jokes on you, my graduation's on first. So congrats to everyone in passing high school. My diploma to the mail. When I earned my PhD, I got my diploma to the mail. They just hand you like a little fake case. I was like, gee, thanks, right? And you actually get the real thing to the mail. All right, so let's get back to this. So logarithmic function is base 10 is called the common log, right? So we're going to call this the common log function, often written by omitting the base. So if you just see log of x, I'm going to say 80% of the time it means log base 10. So be super careful. Be super careful. Careful with the exclamation point. And the reason you need to be super careful about this is there are some physics books, there are some math books where log of x is log base e of x. Okay. And so be very careful about that. Log base e should, here, when we do log base e, we call this the natural logarithmic function. And so that's just written as ln of x. 99, so this is how it's in most modern programs and most modern books. Ln of x means log base e of x. Ln of x always means log base of e of x. So this is safe. However, some older books, since ln's the natural one, this may be log of e. For our class, log of x means log 10 of x, because that's what is standard, okay? So we're gonna graph two different log functions. So let's just do that. So here we already graphed log of 2 of x, so we know what that is. Let's go ahead and put that in. Let's put that in our teal. So let's do this in teal. So here we had at 0, here we had at 2 it was 1, and here at 4 it was 2, and then it'd be here 8, and so it went in like this and came down. All right, so let's do our next one in black. And so let's just get a couple points. So here I'm just going to do a couple random points. How would I get these values? Well, 10 is 1 because it's 10 to the first power. 6, you're just going to crunch your calculator. You just type in log of 6 and you'll get 0.78. We type in log of 4, you get 0.6. We'll type in log of 1, we get 0. We'll do 0.5, we'll get negative 0.3. We'll do 0.25, we'll get negative 0.6. And we'll do 0.1, we'll get negative 1. And so what do we find out here? Well, we find out here, so here we'll plug in, here we go through this point. So all logs go through this point of 1, 0. And the reason is all exponentials went through the point 0, 1. So it flips. So all logs go through this point. Just put in a couple points. So here at 4, it was like 0.6, so 0.6. Here at 6, which is on my thing, be right here, be a little higher. Here at 10, it finally hits 1, so it should be way over here. Here at 0.5, it's negative 0.3. Here at 0.25, it's negative 0.6. Here at negative 1, it's here. And so what this does is it kind of comes in here and crashes and then goes. And so notice here for the higher log, right? So log of 10. So right, this is log of 10, and this is log of 2, x, right? Notice here, the higher the base, the flatter this line is going to be here, and the quicker it lands against the 0, right? So this y equals 0 is a true asymptote, right? And so if I had a log of like 0 point, and then if I did something crazy, so if I did log of 1.1 of x from here, we know it'd be higher up here. So go through this point and go slowly through here. And so we could roughly guess what this is. And if I did here in orange, log of 1,000 of x, it'd pretty much look like this according to us, right? It just looked like a flat line across this, okay? So, yeah, so this is how it goes. And so these are just how different logs look. The natural log would be in here. So the natural log would be somewhere around here or here, a little bit less than 2, but a little bit 10. So all the same graphs, so all of them go through this point. And so this is how log graphs look and operate. All right, so let's talk a little bit about properties, and then we'll do one last little problem, and then we'll go from, and then we'll let you kind of crunch on logs for a little bit, and then we'll do laws of logs. Actually, what I'm going to do after this, since we only have a page to go and we still have like a half hour or 40 minutes of class, I'm going to show you what we're going to do next time. And there's a really good reason for that. I'm going to show you what we're going to do next time. And then it's not going to make a whole bunch of sense because I'm going to kind of just blast through it, but it's going to build scaffolding in your brain. And the reason you sleep is to organize, when you're sleeping, your brain's inputting data into your mind. So when you're sleeping, it's super important for learning, because people who they've done studies where they didn't get sleep before, they couldn't input the data, right? But they did, and so they didn't learn the material. And they did studies where they didn't sleep after. Well, the brain couldn't put it in long-term storage. So one, they just didn't have a capacity to learn in the first place, and the other one, they couldn't crystallize it in the brain. So I'm going to show it to you. You're going to sleep on it, and then when I show it to you again slowly tomorrow, it'll make a lot more sense. So I'm going to use cognitive neuroscience to make sure you guys pass. So after 3 hours of sleep, it's not enough then. Darn you, graveyard shift. Yeah, no, it's the best advice I could give you while going to school is to establish decent patterns, not amazing patterns, decent patterns of self-care, right? Get a little exercise. That's shown to increase your intelligence more than anything else, right? Intelligence is kind of fixed, so get some exercise. It's just good for the body and really good for the brain. Nothing's better than brain than exercise. And you know, those little brain games, go exercise. It's actually better for you. Get a decent amount of sleep. Understand you're gonna have to pull all-nighters. You're in school. It just happens, right? um, and then try to get a set study schedule so you learn over a certain amount of time. I'll pull up something after this and then I'll show you why that is. Part of my class, especially since this is your first intro to college class, is to kind of teach you some basic tools of the trade of how to survive college. One of them is make friends, right? But let's do this and I'll crunch through that and then we'll let you guys go. All right, so the log of base A of anything of 1 is always 0, right? Because 1, 0 is always a point on that graph, right? Or A to 1, no matter what A is, as long as positive, A to the 0 is always 1, okay? A to the A is always 1. What's this asking? This is A to what power equals A? Well, 1, right? A to the X is X. So here, if I want to know A to what power equals A to X, right? Because that's what this is what this log's asking. A to what power equals X? Well, that's X, right? So, and another way of saying that is that this is an inverse function, right? Here, if I plug in f of f inverse of x, I'm going to get back x. That's what it means to be an inverse, right? So here, I'm plugging in log of a to the x, so that's my inverse function, will give me back x. So, and then here's another way of saying an inverse. A raised to, so let me see if I can explain this one without getting lost. X raised to what power? Oh no, hold on. Let me write this. A raised to what power equals x, right? And I don't know what this is, right? I don't know what this is. We'll just say it's q for a second, right? So I get q out of log of x, log a of x, right? But then I'm going to raise a to the q power. Well, a to the q power is x, so that's why we get x back, because it's an inverse, okay? So knowing that, we can do some of these fun little tricks. And so let's evaluate a couple of these things. So the natural log, so remember this is log base e of 1, that equals what, according to this? I'll have you do like 2 of these, since they're simple numbers. The natural log of 1 is what? Yeah, it's 0. Oops, it's 0. And so here, if we have e to the ln of x, well, this is the same as this here. And so that's just going to give me x. Here, if I have pi of pi raised to the 3/4, what's this going to give me? Do you guys know what this is going to give me? Yeah, 3/4 is correct, right? Because this is asking the question, pi raised to what power equals pi to the 3/4? That's what this question's asking, right? Well, pi to the 3/4 is going to be pi to the 3/4, right? Log of 3 of 81. So 81 is so what am I asking here? 3 to what power is 81? Well, that power is 4, okay? Another way of writing this, it'd be, you could say log of 3, and then here you can just write 3 to the 4th, and then this falls out to be 4. This is what you probably see when you actually crunch through it. This is what you're doing in your head. Same here. Here if I have log of 10, because this will equal 1. And here if I have log of 432 of 1, what's that equal? This one right here? 0, yeah, that's 0. Log of anything, log base anything of 1 is always 0, okay? All right, so let's talk about the perception of loudness, right? So the perception of loudness in decibels. So your ear, for very good reasons, and detects magnitudes of sound, right? Detects magnitudes of sound. And so me just barely tapping on this desk is really, really not producing that much power or energy, right? Well, we go to a concert and they're blasting that thing, I went to a Moby concert one time in the Hard Rock Cafe with my brother, and man, that was a bad idea. I didn't bring earplugs. That's a small room, and at one point, let's just say uh, an operatic singer got on and just hit like a high note, and I was right next to the speaker, and I couldn't hear for like a week. So the amount of that was like really really strong, and so we do stuff in this so we can detect powers. And so let me explain this really quick. So so the perception of loudness is given by the following. So our perception of loudness is given by this, and this is actually fairly accurate. This is actually a real formula where I naught is a barely audible sound. So find the number of decibels a sound is that is 100 times that of I naught. And so here we're going to go. So B times 10. So how am I going to do this? Well, it's log base 10 of, well, I naught. Do I know what I naught is? No, I haven't told you what that is. But I told you this is 100 times I naught, right? So if I cross that off, I'm going to get B is equal to log, or 10 log of 100. And what's log of 100? 10, 2. So let's do this. So log of 100, or no, log base 10 of 100, ask what question? 10 raised to what power is 100? So, right, because log of 10 cancels. So this 10 does not cancel out this 10. So there's a very specific reason I chose this problem, right? So this 10 can't cancel out this 10. Inside, I still have to answer this question, so we end up getting 2. So this ends up being 2, so this ends up being 20. Okay. And just for funsies, let me show you the two things real quick. So decibels, how do I spell that? Yeah, we can use fine. All right, so the reason we do this is, so here's a bunch of decibels and things. Does it have a little power quantities? No, it's not telling me what I want. So here we can so here this is something we can barely hear, right? And so it goes through this. So 100 decibels, like massively louder than something barely here. So this gives us the ability to do this. Does someone have, like, I just want a cute chart. No one has a cute chart. Fine, I'll just look at images. Someone has a cute chart. There we go. So yeah, so healthy normal theory. So 0 decibels is something you can barely audibly hear, because if it's I naught over I naught, that gives us 1, right? Rustling leaves about 10, whispers about 15, light rain, quiet office, normal conversation. So I'm probably speaking, well, let me tell you exactly where I'm speaking at. I am speaking at about 60 decibels, because I have my little watch tell me. But notice how it ramps up really hard, because my voice isn't producing that much power, right? A toilet flushing or a vacuum cleaner, that's a lot more power. That's like an order of magnitude more power, but it's only 10 more decibels, right? Heavy traffic, cars make a lot of noise, and so that's a lot more power. A sander is really loud, right? And then a hand drill, chainsaw, riveter, jackhammer, um, fireworks, you know, shotgun blast. This is why you wear protective stuff while you're um, sh- shooting guns and stuff. And so, let's see if I can get another one. Airplane, maximum crowd noise. Yeah, so this is decibel. So logarithmic scales are very, very useful for determining stuff of different powers. Yeah, the seismic scales are like that. So if you have a massive range, if you have a massive range between what is the weakest you see and what's the most powerful thing you see, kind of like you can do it for light as well, light intensity and all that. A logarithmic scale makes a lot of sense to define it. In fact, our brain, in order to make sense of it all, does a logarithmic scale. So we actually do a logarithmic scale when we hear things. It's actually a logarithmic scale.